discuss about the three-dimensional kinematics of rigid bodies. We'll discuss the rotation about a fixed point and the time derivative of a vector measured from either a fixed or translating rotating system. First, rotating about a fixed point. Before that, we must learn about the radians versus degrees. Radians measure angles as the ratio of arc length to radius. One radian equals approximately 57.3 degrees. Radians simplify many rotational equations and are preferred in engineering calculations. Conversion formula is theta radians equals to theta degrees times pi over 180. Direction of rotations. Positive rotations follows the right-hand rule. Counterclockwise rotation viewed from the positive axis is considered positive, while the clockwise rotation viewed from the positive axis direction is considered negative. This is crucial for consistent vector analysis in 3D rotational problems. So if you're having problems with your solving, you can construct an illustration of it in 3D form so you can visualize your problem to solve it better. Next is angular velocity. It describes the rate of change of angular position with respect to time. If the body is subjected to an angular rotation d theta about a fixed point, the angular velocity of the body is defined by omega equals to the change of theta. The line specifying the direction of omega, which is collinear with the d theta, is referred to as the instantaneous axis of rotation. Angular acceleration, the rate of change of angular velocity over time. It is the change of omega or the angular velocity. So acceleration is not directed along the instantaneous axis of rotation. Average versus instantaneous. The average angular velocity is equals to the delta of the change of theta over the change of time, while the instantaneous angular velocity is equals to the limit of change of t to zero and d theta over dt. Vector nature of angular velocity. It represents as a vector along the axis of rotations. Its magnitude equals to the rate of rotation and direction follows the right-hand rule. The vector representation allows for 3D analysis of complex rotational systems. Resultant angular velocity. Since d theta is a vector quantity, so too is omega, and it follows from the vector addition that if the body is subjected to two-component angular motions, the omega sub 1 equals to theta sub 1 and omega sub 2 equals to theta sub 2. The resultant angular velocity is omega equals to omega sub 1 plus omega sub 2. Velocity. Once the angular velocity is specified, the velocity of any point on a body rotating about a fixed point can be determined using the same methods as for a body rotating about a fixed axis. So the velocity is equal to angular velocity times the radius. For the acceleration, if the angular velocity and angular acceleration are known at a given instant, the acceleration of a point can be obtained from the time derivative. Acceleration equals to angular acceleration times radius plus angular velocity times the product of angular velocity times the radius. An example problem: a solid disc of a radius of half a meter and a mass of 4 kilograms is mounted on a horizontal axle through its center. A force of 10 newtons is applied tangentially to the edge of the disc. What is the angular acceleration of the disc? So it is a solution. We will solve the torque. Torque equals to force times the radius, which is 10 newtons times half a meter. We have 5 newton meter, and the inertia, our inertia is given by 1/2 times mass times radius squared. So we have 0.5 kilogram meter squared, and to find the angular acceleration, we will derive it from the formula. Torque equals to inertia times acceleration, and then acceleration equals torque over inertia equals to 5 Newton meters over 0.5 kilogram meter squared, which give us 10 radian per second squared. Next is the time derivative of a vector measured from either a fixed or translating rotating system. For a general vector q, state the relationship between its time derivative in an inertial frame s sub 0 and its time derivative in a frame s that rotates with an angular velocity of omega. So our formula is here: dq over dt, so s sub 0 equals to dq over dt s plus omega times the q. Omega is the angular velocity direction given. Its direction is given by placing the heel of the right hand at the axis, curl fingers in direction of rotation. The direction of the angular velocity is given by the outstretched thumb. So here our dq over dt as sub theta is the rate of change of q as seen in inertial frame s. Well, the one below is the rate of change of q as seen is a non-inertial frame s. So our illustration and our example problem: a rotating frame R spins with a constant angular velocity omega equals to 2 k-rads about the z-axis with respect to the inertial frame F. In the rotating frame R, a point particle has a velocity of 3 i/ms. What is the velocity of the particle of the inertial frame F? So we'll use the formula as was shown before. We'll plug in the numbers and we'll cross multiply the products, and it gives us the answer of negative 5i meters per second. That is the velocity of the point particle in the rotating frame F. Thank you for listening.